Hello everyone, and thank you for coming. I didn't expect so many people would want to listen to me to such probably a boring, pure science and engineering topic. But I have a little bonus, because there is one idea behind this presentation. And if you could bear this, if you could withstand this presentation, I'll tell you it in the end. But let's move to the topic. Just a little bit about myself. I'm a student, a master student from Bauman Moscow State Technical University, BMSTU, Russian oldest and leading technical university. Our department, Computer Systems and Networks, is both about software and hardware. That means that this theme is very close to us. Because you know that electric chains, that bores can be represented as graphs. So let's move. The problem, for example, where can we use graphs? For example, in science, it's bioinformatics. In industry, I mentioned it's some boards and also networks. Because you know that path discovering in network is a graph model. Okay, but graphs are different. In bioinformatics, they use de Broglie graphs. In electricity, they use hypergraphs, etc. Different types of graphs for different things. And also, please note that graph can be directed or non-directed, etc. But when the problem began? Probably in 80s, because first, not really multi-core, but probably first kinds of clusters, first kinds of parallel programming, and it's a real problem, because the model of representation, its basic, are really old, probably since 1978, I suppose, and the basic model, you know, is adjacency matrix. And you have some techniques like PGS, but it's really hard to distribute such model. And computer systems have changed dramatically for 30 years, and that's why I think that current models based on that model, on passive data structure, are not very efficient, very inefficient for now. Yes, ineffective resource usage. So, what's next? Load balancing, as I mentioned, especially dynamic load balancing, is a big problem. Because sometimes you have statical graph. You don't have to rebalance it, but just think about some electric scheme, or for example, about network. You can add some hosts, you can add some routers, and probably sometimes on one node, on one computing node, you have too many nodes, too many vertices, and you have to rebalance, but it's very difficult if you have passive data structures. Representing graphs in heterogeneous systems. It's also a big problem if you use native languages, because you know different CPUs, different operating systems, etc. Multi-user problem. Sometimes I want to read data, I don't want to change it, and somebody else. But most models are synchronous, and I can't run two tasks in a time. And it's really a problem. It's an effective resource usage. Because, for example, I have vertices I need on node number 1 and other person on node number 3. But we have only one interface, and unless I get my information about what vertices, the other person can't get to node 3. So one node is working and other nodes are not. A little bit about traditional models. I know there are plenty graph representations models, and some of them are really new based on MapReduce and Hadoop. I'm a little bit familiar with them, but I tried to explain that they share the similar basic idea, and I really don't like it. So they use passive data structures. I mentioned they are matrices, some records, sometimes they are files, etc., but they're passive. They can't do something by themselves. It's a reference to Butch. He is active and passive objects. That's why I call these passive data structures. Yes, and they can be bottlenecks because, as I said, they can't do anything by themselves. There are plenty of entities, plenty of vertices, and I have to manually handle with them. That's pretty bad. They're synchronous. That's a problem I also described when I want one operation and I can't do something else before I got results. That's really bad. Also, sometimes you need asynchronous operations. For example, my model is static, no changes, and I want few results for different operations. I don't really care where I have a result. I don't care the order of results. I just want them. And I need asynchronous model. I can do synchronous model from asynchronous, but vice versa is not true. So, possible solutions. Because, as I said, our computers have changed dramatically and we have new techniques. So, virtualization, it's a modern trend and our hardware is really ready for it. Then you can run multiple more than number of cores, threads or lightweight processes in our case. For example, you can only have 2 cores, but you can have thousands of processes, and it also can solve such problems as heterogeneous representation for heterogeneous systems, I mean. Asynchronous model, I described it already, let's move. Using lightweight processes instead of passive data structure. I think this is really a solution for load balancing, because in one case, for example, I have 2 baskets with eggs, and if I have passive data structures, I have to say, okay, I just take this egg, and move it to another basket. But if I have active data structures, they can move by themselves. That's okay. And our performance is increasing. That's good. And hierarchy for horizontal scalability. Because, you know, some modern models, like CUDA-based model, their horizontal scalability is pretty bad. Some models like MapReduce model or Hadoop model, yes, they have a good scalability, but not as well. So, language, I suppose you know already. Of course, Erlang. Why? Because, first of all, lightweight processes. It's really easy to migrate your vertices to perform load balancing using Erlang. Next, it's scalable. And I showed you proof in the end, in the experimental part. And as a good side effect, a positive side effect, it's fault tolerant. And it's really good for Beowulf clusters and for grid computing. Some notations, you probably know some of them. First of all, it's supervisor. It's a process who is responsible for fault tolerance of its child processes. The second notation is worker process. They're just simple, plain worker processes, nothing else. The plain line is connection between 2 nodes, and if somebody is a parent of another process, we'll use such type of line. And the second type of line, probably we won't use it. It's a connection between processes if no one is a parent or supervisor for another one. And it's connection between resource and its owner. And the third, we'll use it. It's dotted line. It's a connection between remote nodes, between remote vertices. Also, please know that we will use arrows for direction of message passing. So, I've thought already about this model is hierarchical, but if we have hierarchy, we need the root, and we have 3 levels. First of all is global managing level. On global managing level, you know such thing as structure of graph, how many vertices, which vertices you have, but you don't know bits of processes. So you know only general information. You will see it later. Second is local managing level. Local managing level, it's about computing nodes. We have different type of nodes. There are computing nodes, there are nodes on which vertices are allocated, and there are managing nodes. There are nodes with interfaces with user. And workers level, it's our vertices. So, this is a simple example. It's not full. Here you can see one managing node called master node and one computing node with 2 vertices. Please note that vertices can send messages to communicator, but we don't show arrows from vertex to communicator because sometimes there are thousands of them, and I think that thousands of arrows from vertices to the communicator is not good. So it's an exclusion. So master process. It's responsible for everything. It's responsible for fault tolerance of most required processes. I said most, but not all. We'll see it. And it's also interface for interacting with user. It shows at least 2 ETS and 1 dead stables. The first dead stable is graph, because we have to store somewhere our model. So we use this GraphDB usually only for graph allocation, and usually we use it only 1 time, and probably 2 times to write some changes in structure. The second one, vertices. Adds and type set. It contains association between vertices and nodes, I mean computing nodes, where vertices are allocated. And nodes. This is info about our computing nodes. Type set and contains associations between nodes' symbolic names, usually they are atoms, and bits of their communicator, because communicator is the root of computing node. So communicator, as I have already said, it's the root process of computing node. By default, only by default, it owns only 1 named at table, local vertices. Type of table is set, and we have following columns. The ID is Vertex unique ID. PID, that's process ID on this node. Local, that's very interesting column, because we have to count for load balancing how many connections do we have on this node, and how many connections we have with our nodes, because it's a default condition for load balancing. If vertex has much more connections with another node, sure, it have to migrate. And n-1 columns entitled like Node M, where N is a total number of nodes, M is the name of another node. For example, if you have 3 nodes, on node number 2, you will have columns, of course, VID, PID, local, and then node 1 and node 3 with number of connections to these nodes. Vertex. It's very simple. It's a worker process. Maybe font is... It's okay. It's a plain worker process. It doesn't own any resources, but it has its state, which can be described by VID, I already mentioned it, CPID, it's PID of parent communicator, list of current tasks, contain task ID. Soon I'll tell you about transaction server and how tasks are executed in this model, but it's just a list of integers. List of connections. It's list containing tuples like cvid for connection VID is VID for Vertex connected by outgoing connections. PID, it's this Vertex speed. EID, it's edge unique ID, it's atom, and weight of edge. Last 2 columns are not necessary, and by default EID is U1 and weight is 1. So if you don't want to, probably you don't have a directed graph, so never mind about it, it's okay. And I have described it. List of neighbors is the same but for incoming connections, and it's empty for all types of graphs except directed graph. So transaction server, because you know we have to track our tasks. Transaction server is a required process on master node. It owns by default 1 adds name table tasks. Record in this table looks like TID, stands for task ID, operands, tasks, and status, where TID is a unique task ID, it's an integer. Operands, it's a list of communicator speeds of nodes where operands are allocated. But we have one exception, it's for coarse-grained tasks, but you can address 2 exact vertices, not only 2 nodes. Task is tasks short description, you'll see it as example giving max weight. And status, by default it's list, and when task have just started it's empty, but if one node executed its task and sent a message to transaction server that okay, here is the result, I have performed it, and transaction server adds this node name, its symbolic node name, to status, and it can be atom okay when all nodes completed their task. It should be okay, that means that this task is executed. Later I'll show you why do we need it. Also please note that transaction server is not necessary for some operations. It's a very flexible component, and please note that most components in this model can be changed where logic is extremely flexible, and I'll show it when I'll tell you about support processes. But by default some kind of tasks, they're called direct tasks. They're not recorded on transaction server, like if you add an edge or if you want to remove some vertex, it won't be recorded. But you can change it if you need a full changelog. So they were required processes, and now let's do support processes. That's why my model is extremely scalable. SupportMaster is just a special type of support process for solving multi-user problem and for reservation. Why? Because it owns copies of master nodes tables, but only all required. Soon I'll tell you why only all required tables. So by default, only 3 tables I have described earlier. It can do most of master processes functions, but it's not responsible for fault tolerance of our nodes. Also by default, because master process can die and one of support masters just can't replace it. Support transaction server, yes, because transaction server is necessary. And if you spawn a support master, you'll automatically spawn a support transaction server. How do it work? It works. Because when you spawn a support master, there are 2 ways. You can just spawn it on different node by yourself, or master node can spawn it and be a guarant of fault tolerance for your support master. And support transaction server is a reservation for transaction server. It owns the copy of transaction server's all tables. And it's a named processes. They are transaction server and support transaction server are named processes. They are registered for, you don't need to know their PIDs. It's connected to transaction server directly, and it's automatically created after creation of support master, and connection between support master and master is similar to transaction server and support transaction server, because their tables have to be synchronous. Before we move to GSP, just one example, because TSS is a flexible component. How does it work? For example, I want to perform some action through support master. I invoke some interface function. It sends a message to support transaction server, and then support transaction server looks at its table called tasks and decides which task ID should I use. By default, it's next. Then he asks its master, transaction server, can I use this TID? And transaction server can reply, oh no, it's already equipped. Okay, then I try to use another, and so on and so on. But logic is flexible. You can just have some range of task IDs for nodes. You can change it. So the other group of support processes are service processes, or global support processes and local support processes. Let's start from global support process. Yes, GSP stands for global support or service process. Any support process created on global managing level is support process. It's GSP. It can be, for example, a process which provides some web command line interface for sending commands, and also if you want to visualize your results, your OpenGL server will be also GSP. I think it's clear. So the same story for LSP. It's a support or a service process on a local managing level. So they don't have any access to global data, but they have access to local data such as PIDs of vertices. That's why GSPs are not enough for our model, and we need to have LSPs. Also, GSPs and LSPs together are a powerful tool for data reduction, and I'll show you this later on an example. Yes, they're flexible components, and we have only two restrictions. First, please note that your support processes shouldn't decrease fault tolerance of the whole system. Let it crash, but don't let it crash the whole system. Also, please note that support processes should be on their places. For example, when you spawn web CLI on global managing level, it's okay, it's normal, but spawning the same process on local managing level is not. So just another simple demonstration of model, but you can see transaction. Oh, no, transaction server is on its place. There are two nodes and one remote connection from vertex number 2 to vertex number 3. I think it's clear. So, about fault tolerance. This model is good for clustering, and I suppose it's also good for grid systems. Why? I'll show you. First of all, I've already mentioned it. Let it crash, isolation. Okay, all vertices on one node can crash. Communicator will respawn it. Communicator can crash. Master node will respawn it. It's okay. Second is task fault tolerance. For example, you have 9 nodes and you want to execute some tasks. 3 nodes have finished their task. One node, probably, 6 nodes have failed. Okay, we have message that 6 nodes have failed, and master process just send transaction server their symbolic names, and then transaction server will find their names in its tasks table, and it will just resend them a task, and we will try to execute it again. But you still own results of previous third nodes. It's okay, you don't have to re-execute these tasks for all nodes, just for fallen nodes, just for failed nodes. And it's reservation because a SupportMaster can become a master. For example, if master failed, you can just say on one SupportMaster, okay, now I am a new master, and that's okay, the model is the same, and TSS on this node will become a most transaction server, a main transaction server. About load balancing, there's a simple algorithm. Of course, it's just a basic. First of all, we have a communicator or LSP which tracks how many remote connections do we have for each of our vertices. That's why we have columns entitled like local, etc. If it finds that some vertex has more connections with any other nodes, communicator sends a message to this node. Remote communicator receives this message and it decides, can it spawn a new process or it can't. So if it can, it sends back a reply that, okay, I have spawned a process, its new PID, you can start migration. If communicator receives approval, it passes the message of reallocation to this vertex to be reallocated. Next, the vertex process enters the state of migration. It's the special state. The vertex won't execute any commands. It's just will pass it to mailbox of new vertex, and it will send all processes from list of neighbors and list of connections its new PID on remote node. And communicators of connected processes update their vertices table on this step. The vertex processes sends its same VID, list of tasks, a list of connections, and a list of neighbors to the new process. After that, the new process registers in the remote node's local vertices table, and we have to sends messages to communicators and to master nodes and of course to support masters, that allocation of our vertex has changed. Let's move. We have initial allocation task. That's why we need GraphDB. We need to allocate our graph, our vertices. We have a special type called search agent. I didn't mention it because it's temporal and it's flexible. First of all, master process creates SA and sends to nodes its PID and task of initial allocation. Then nodes send messages to SA to get a portion, so some bunch of vertices to allocate. And they say A tries to find this portion of vertices, and it tries to find vertices which have minimum connections with other nodes. For example, if node 1 asked for a portion, support agents will try to find as many nodes connected to node 1 as it can, but not to node 3, not to node 5, etc. So, some performance tests. I have used two nodes. First of all was its desktop computer with CPU Intel Core 2 Quad at 267 GHz, DDR2 8 GB of RAM, and Windows 7 Home Extended. And another node was a laptop computer with one. So it's not interesting. Let's move. First example, you can see some model of electric chain, and I wanted to find a max weight of some edge. I want to know which edge is the heaviest. So what should I do for it? First of all, I should create a GSP for data reduction. Then I'll pass its speed to all communicators, and I pass them task of max weight. All communicators will spawn LSPs, same for data reduction, and send its PID and task to all vertices. Vertices try to find the heaviest edge in its list of connections and list of neighbors, list of connections only, and then pass it to LSP. LSP knows how many vertices do we have, and it will wait while all vertices will send their max weights. Okay, and the same story for GSP. It will wait when every node will send results. LSP reduces data on local level. We need to find first of all a local maximum, and GSP then finds a global maximum and passes it to master, and we got the result. Let's have a look. I have few tests. As I said, the previous algorithm is unoptimized. Why? Because, for example, we can pass a message directly to GSP, first of all, and also you can see there is a bottleneck, because I push by default only one vertex on node, but I can push more than one, because as you can see, vertices 1 and 6 are really bottlenecks. So optimized algorithm fixed these small lags, and another implementation is unoptimized algorithm on Erlang R17.3. So you can see that model is scalable. It's only for one node experiment, but growth is slower than linear. We'll see it. here we go. You can see, for example, when 15 vertices and 500 vertices, not, let's say, it's slower than linear, and that's all. Also, I have some experiments with remote nodes, but when they're both two local nodes, we have similar results. For example, look at 500 nodes on two local R15B03 nodes, the similar time. And if we use Wi-Fi connection, we have a lag, we have latency. Let's move to the next. This is really an important example. It's inspired one of my mates from Uppsala University, and this is a real example of searching a path in deburring graph. It's a task from bioinformatics. This is about genome assembly. For example, I want to find a chain from gene A to gene B. There were some restrictions. I used only binary alphabet and no more than 1024 vertices. But such genome, it's applicable for some simple animals or some simple plants. So it's okay, it could be a real performance. You can see average time of searching path. It's also slower than linear, probably, we'll see. Average time of processing vertices. That's why model is scalable. You can see it's constant. It doesn't matter how many vertices you will have. No overhead for scalability. Or usually we have a little, but it doesn't matter. It's very little, it's very tiny. You see, it's look like constant because it's in microseconds. And average time of searching one vertex in path. It's very complicated parameter because it looks like average time of searching path divided by average time of processing vertices. So before it's completed, I would like to say a little afterward. I promised you a little secret. So I have one idea about. I really like functional community. Guys, I can see that you are open-minded, that you are brilliant, and you are curious, because you know functional programming is not a mainstream. So you're trying to discover something new, and it's good. Be curious. I was curious, and I looked through many books, and I saw that synchronous model, and I said, no guys, it's wrong, it's awful. And you saw experiments, and I see that my model, at least this time, it's better, and I just was curious, and that's why it was possible to invent, to design something new. So be curious, ask questions, and if you don't trust some science problems, find a way and check it. So feel free to ask questions and send your feedbacks, probably not now, but I will be very happy to have your feedbacks, your questions, your ideas, etc. So my mail and my Twitter, you can see it. So thank you.
Okay, so we have time for some questions.
So I noticed that your graph searches were constant time, and I know that's the case if you're searching for a path that contains A to C and B is along the path.
You mean which? You mean that constant, the red line? Yes.
So if you're doing searches that are more graph analytics, where you have to say, give me all of the people who have blue eyes, who have watched this movie and rated it highly. For graph analytics, overall graph processing type stuff, do you still have the speed, even though it's distributed?
Yes, it proves that it's scalable. Why? Because this red line is its average time of searching path of executing task divided by number of vertices. So, for example, I can divide. It's just an example. They are not exactly. So I can execute this task on 30 nodes on 30 vertices for 10 seconds, and I can execute it on 300 for 100 seconds. And yes, it's linear scalable, it's constant for one vertex. That's the idea. That's why I wanted to show it to you. So no overhead for growth. Did I answer your question?
Maybe. I'll follow up via email.
Okay, I'll be happy.
Okay, some more questions? Okay, so let's thank Iurii again.
Let me take